Hello everyone, welcome to the next lecture on system programming, your favorite course of lectures about your favorite topic. And today is the lecture about processes, work modes of the processes, their memory layout, resources, interrupts, how do they communicate with the kernel, how do system calls work. On this lecture we will follow this plan. We will first look at what is the process again. We will see how the processes appear from the system call fork. Then we will see how memory layout of the process looks like. Then we will learn how file descriptors are working, pipes, how do the processes get interrupted, and how do system calls work. On the previous lecture we talked about briefly all the subsystems that we could locate in the kernel, which could possibly be interesting to us in the Linux kernel specifically, and you can see them on the slide. The time subsystem we have already seen completely, and we also started the processes subsystem, and we specifically considered the topic of the process scheduling or task scheduling. And today we will dive a bit deeper into the processes. First of all, what is a process? It's a working program, you can say, but it's not the only thing it consists of. It's not just the code which is being executed. The code is stored actually in memory, and the memory of the process not only has the code, it has multiple sections besides the code itself. Firstly, the code, it is stored in memory, so as it could be executed, and its memory section is called text. It also has other sections, like for example for storing global variables of some sort, initialized, uninitialized, and it needs some memory for the stack. So the thread could be putting your function arguments on something and work with some local variables on that stack. And also needs heap for long-term allocations. And when you have multiple tasks, multiple threads in one process, then you will also have probably multiple stacks. And in addition to memory, process also has other resources such as file descriptors, signal queue, and inter-process communication means which might belong to the process. The signals and EPCs we will look at different lectures, and today we will look at the memory layout and file descriptors. Also, the process is a virtualization mechanism. It's not just a bunch of memory sections. The purpose of the process of the task in Linux kernel is virtualization. So it allows you to execute code, not thinking at which physical CPU core it will be executed and how much memory your machine has. Because when you write code, you usually don't think about how much memory your machine has, right? You just allocate memory, you free it, and you have the entire address space from 0 to 2 in the power 64 minus 1, and you just use it. Because the actual physical memory is virtualized from you behind this virtual memory, at which we will look also at separate lecture. And also the process allows you to not think about how many CPU cores you have. You can have 1, 8, 32. You usually don't think about that much. You might be thinking about this like in terms of how powerful hardware you want to buy or something like that. But otherwise, when you write code, you usually try not to depend on how many CPU cores you have, because process allows you to abstract this physical layer away. In the kernel, each process, thread, or task, again, from the previous lecture, you should remember that the Linux kernel operates on tasks, and on top of tasks, it builds constructs such as processes and threads. So in the kernel, when you have a single process with single thread, it will be represented by a single task struct. And you can see it on the slide, and we saw it already before, and we will see it a few more times. And I will just remind you that it stores metadata of the task, such as you can see stack pointer, for example, its memory sections, the struct object, its exit state if it has already exited, its process ID, parent, children, tasks, when it was started, credentials, file descriptors, and so on. And every process, such as this task struct, it is created from fork system call. The fork system call allows to duplicate the caller process, or caller task, I would say. If a new program should be started, it always starts from fork of an existing process. There is no way to start a new process completely fresh from some executable file, for example, like in Windows it's possible. In Linux it's not. You always have to firstly copy some existing process, and then in the child process you can already execute something new, such as you can call one of those exec system calls, which take the path to the executable file, the arguments, some environment variables perhaps, and some other options. There are many of those exec functions. I recommend you to just look it up yourself in documentation, how they work. I don't even remember it myself, because it's not so frequently needed. And the child process starts a new program by the path that you have given it, and then it becomes completely new program. And then eventually the process will exit, like finish its work, and it always ends with exit system call. And when it's done, the parent process can collect the exit status of the child process using system call wait. This means that all the processes are relatives in the system, because always to create next process, like a new process, you need an existing process to create this one, which means if you go up this chain of process creation, eventually you reach some top, some first process which should be created initially probably by the kernel, and that process can already create everything else. And this process exists in Linux. It is known as init process. It has PID1, and in Mac you can also find this process. It's called launchd. And you can find it in the sources of the kernel. It's literally a kind of a global variable, which is just created at compile time already. And when the kernel starts, it will show this initially created static task as the first process. It has no machine code. It's just something, it's like a dummy top of the tree to which the child processes can refer to as their parent. And this means the tasks, the processes in the system, they, in Linux at least, they're all organized as a tree, where from any node you can reach the top eventually if you go to the parent, to the parent, to the parent, and so on. Now let's see how fork creates a copy of a program. Copy means complete copy, like with all the same memory, with all the same code to execute, and we just want to test how it works. So I wrote here a simple program where I do the following. In the first lines, I call fork, and I expect that now there are two processes, children and parent, and they execute the same code. If they execute the same code, how do you make the child process execute something new? Which means the processes have to kind of know who of them is child, who is parent. So as one of them could continue one path and another one could continue another path in the code. And this is done in a way that system call fork will return different values in the parent process and in the child process. In the child process it will return 0. It means if it's true, this condition was checked in the child process, and based on that you can do something like execute child specific code. In this case it's not very complicated, we just print something and return the code 100. When the fork returns something greater than 0, it means the check was done in the parent process, and based on that you can also do something. In our case, we just wait for the child to get finished. We make the system call wait, and it will block our thread until the child process is finished. And when it's done, we will print the result. Note that I'm printing the result using a special macros vExit status. The thing is, when you call wait and get some result, the result is not the exit code of the child process. It's actually a bit mask which inside contains the exit code. If you know that the process exited gracefully and it has an exit code, then you can extract it using the macros vExit status. And there are some other macros which you can also look up in the documentation for other different reasons of exit. So for example, a child process perhaps was killed by a signal. For example, it got a segmentation fault. Then it was a segmentation signal zigzag, or it was killed using sig kill. right? About signals we will talk a bit more, but right now we only look at the graceful exit, when you have an exit code and you can get it using the exit status. And when we run this program, we will see the output that a parent was started, and then it started the child process, and the child process printed something, and the PID of the child process is different. You see it's 45602, while the parent was 45601. Then the child says that it was terminated with code 100, and we see that the parent eventually waited for the child to finish and got the result to 25,600. This is not the return code that we did 100, but you can extract it using the exit status and you get the returned child code was 100. This is how you can extract the exit code. And I have a question for you. As you remember, this slide with a lamp on it means that this question is supposed to be answered by you. You have to think about it, put the video on pause. And the question is, why is fork fast even in big processes? It's not the answer yet. I'm just explaining the question. The thing is that fork, we see logically that it's supposed to create a copy of the calling process. Like complete copy with all the memory, with all the code. And it works fast, even though sometimes the processes can be quite big. Like they literally can take multiple gigabytes of the main memory, and they can have a lot of code, like also hundreds of megabytes or even gigabytes of machine code. And nonetheless, the fork still works fast, kind of. So you can have a process like our previous example, you can have a process of a size like 10 gigabytes. Fork will work quite fast in both of them. And it will not really, when you will check out the memory usage of your system, you will see that the copying actually didn't happen. Your memory usage of your computer did not grow like 10 gigabytes if you made the fork in a process which was 10 gigabytes of RAM. How do you think fork is working so fast even in large processes? Time to think, put the video on pause, and when you know the answer or you give up, resume the video. And the answer is copy on write. This is actually a common design pattern. I don't know when it appeared first in the kernel and then it was spreading more, or it was an older pattern than the kernel itself. But the idea is when you have to create a copy of a large object of any sort, like for example a process in a system, you don't need to create the copy right away instantly when it's requested. You can instead make a copy on write or copy on update. So when, specifically in the kernel, it works this way, that when a process calls fork, the kernel will not copy everything at once. Instead, it will mark memory of that process as like with the special flag that when a next write will try to happen at this memory in this process or in the child process, then it has to be copied. But until the memory is being written to, it will not be copied. That's why it's called copy on write. The copying does happen, but only on write. And not for the entire memory, by the way. The memory of your process, it is split into, like, we will talk about it a bit more in the next lecture, but the idea is memory is split into kind of pages of limited size in the main memory. And the kernel will mark each page physically in main memory with a special flag. So when the main memory device receives writes from the CPU, it will reject those writes and send an interrupt to the processor. And the processor will see that there was an attempt to write into a page which has copy on write. And then the kernel will copy the page and will change the mapping of those processes so they start pointing at different physical memory. And then it will happen for every page, not for the entire process at once. So it's not only copy on write, but it is also like incremental copy. In small portions, the memory will be copied on demand. This is how it can work, like visually. You have parent and child, and the fork just happened, and they have, imagine, a variable a, which is equal 100. Then at some point, child wants to assign a different value to variable a. The variable a is stored in some memory page. So the CPU will try to send an instruction a assign 20 to that memory page, to your memory device. And then it will receive an interrupt from the device, and the interrupt handler in the kernel will see that the reason is copy on write, which was triggered by write, and then it will copy the page, and now two processes will have different pages for the same variable, and they are not connected anymore in this page. Needless to say that the processes will not even notice it. When you write code, all of this is happening under the hood, and the kernel doesn't even have to notify you. You just write your code as usually, and then the kernel under the hood, when it's needed, will copy the parent's memory into the child process or vice versa, when they will start having write access to those pages. Let's return back to our previous example to test how this memory thing is working. Here in this example, the same one, I also in the beginning of the program, before the fork, created a memory block filled with zeros using calllog function. And what then I called fork, which means this mem pointer, it is shared right now by child and parent. So they kind of, right after the fork, have this memory the same. And then in the child process, I set this memory to ones instead of zeros. And then in the parent process, I will print the memory. And we will see that in the parent process, the memory did not change. Let's look. So the parent was started. It created the child process. The child process did set the memory to values 1. Then the child process was terminated and the parent prints memory values are 0. So the parent was not affected. When I called memset in child process, the memory was copied. And it was exclusive to the child, and the child just set to ones its own memory, not the parent's memory. Besides fork, there is one other way how to create copies of a process. It is a system call called vfork, or like probably it means virtual fork. And this thing will not enable copy on write. And it works even faster because of that. Because even just enabling copy on write can take kind of a lot of time. Because like I said, yeah, you don't need to copy all the memory actually when the fork happens. But you need to mark all the memory as like with this special hardware flag. So when the write does happen, it is noticed and the copying can be performed. Which means if you have a very large process with, let's say, hundreds of gigabytes of memory even, then it will have to walk all the pages of that memory, which can be like hundreds or thousands of those pages, physical memory device, and set the flag for them, and it takes a while. So yeah, you will not have to walk to copy everything, but you need to like iterate a relatively long loop and execute some relatively expensive hardware operations for regular fork, and it can be noticeably slow in large processes. vfork allows you not to enable copy on write and it's very handy thing when the child process after fork would anyway immediately just call an exec function, one of those exec functions. So we don't need a copy really. We just need to create a new process which will run a completely new program. So why would we want to copy the previous memory of the parent? We don't need that. That's why vfork exists. It's a little bit more dangerous because literally you can stumble into a lot of undefined behavior situations when you call vfork and then the child process suddenly between fork and exec, for example, tries to locate something on the heap or tries to access some global variables and change them. Since the memory is shared with the parent, this way you are going to screw the parent process. You should not do that. And also another downside is that when you call vfork, the parent process, like the parent task, is blocked like frozen, stopped, until the child process either exits or calls one of those exec functions. This way, the kernel tries to guarantee that two processes at the same time will not try to run on the same memory. So right after we fork, you should ASAP go and do an exec or exit so the parent can continue. This is like a trade-off. So instead of paying for, you pay this constant overhead for how long the parent will be blocked instead of paying the dynamic overhead of having to mark all the memory pages as copy on write. It can be useful in really large processes. What happens, do you think, if the parent process does not call wait? As you remember from the previous example, and I showed it already a couple of times on this lecture, when the process is started, it always starts with fork, then it optionally can call exec, then it calls exit, and then the parent has to call wait to collect the exit status. What happens if the parent process does not call wait? Then the process becomes a zombie. It's a special mode, like officially named zombie in Linux, in which the process is present, like in this state, after it has exited, but before the parent process has collected its status using wait. Only after wait, the zombie process resources will be freed and it will completely disappear from the kernel. The reason is that when the process exits, you normally want the parent process to know how did the child exit. What was the exit status? What was the exit reason? Was it a signal, stop? Which signal, if it was a signal, and so on. If the child process would just instantly delete itself after exiting, like completely disappear from the kernel, then the parent would have no means to find how did the child process exited. Was it a success? Was it a failure? And this is why the child process has to stay for a while, like linger in the kernel until the parent will notice it and will call wait and get the exit status. Until wait is called, the child task will take memory in the kernel, at least for the storage of the task struct itself. The memory of the process, like all its heap stack and so on, will be of course freed and it will not be executed anymore, but the object task struct will still be in the kernel until you call wait. And also the child process will take process ID, a unique one. And no other process can use this process ID until the zombie process is like terminated finally. It can be a problem if you have a long-living program which creates a lot of zombie processes. You can eventually actually exhaust your unique process IDs and the system will stack. If the parent process was terminated before the child process, or even after the child process, but it didn't call wait at all ever, then after parent termination, the zombie processes all get inherited by the process init, by the system itself, it means. So the kernel will collect the zombie processes if nobody else can collect them anymore. But when your parent process is alive, you should be calling wait. If you don't call wait, you will end up with zombie process. You can check out which zombie process you have in your system using command ps, which will list all of them, and the zombie processes will have special status Z. It means this is a zombie process. On Mac you can also observe them. They will have state Z plus, or just Z maybe, but I only saw that Z plus. And the status, like on the right from the name of the executable, will be called defunct. So it's not just a Linux thing. I don't know if it exists on Windows, but on Mac and Linux it absolutely exists. And you can create a zombie process very simply, like by mistake or by intention, but it's very easy to start creating zombie processes. On the slide you can see a very minimalistic example where I create a zombie process for 15 seconds. It's very easy. I just make a fork and then the child instantly exits. So just returns 0 from main, and then for 15 seconds I do not call wait. When I finally do, the zombie will disappear. But until then, for 15 seconds I have a zombie process. I also said that the processes are terminated using exit system call, always. Even if you don't call it yourself, it is always, each process is terminated with exit. Even when you just return from main function, the still exit is going to be called later after the main function returns, because main function, it's not just like when you return from main, the program doesn't really exit right away. And also main is not even the entry point of your program. The execution of your process, of your code, doesn't start with main. It starts a little bit in another place. And after main, it will continue execution of some other bookkeeping things to destroy and free some memory and finally call exit. The actual entry point into your program, at least on Linux, is a symbol called underscore start. I call it a symbol because it doesn't have to be a function. It just has to be some address to which execution can jump. So, but in C we can actually imagine it as a function. And this code on the slide, it will actually compile and run, even though there is no main function. And you can build it in a special way. Like normally when you just compile any code, it expects that you define main function. And the code before the main will be generated automatically by the compiler. But you can also tell the compiler not to do that and give control right away to your custom start function, start symbol. For that, in GCC you can specify no start files option, and then it will compile and run, as you can see on the slide. And in Mac it is also possible, except that it has a little bit different options. Like you have to give the symbol name explicitly yourself and start it with an additional underscore due to how symbols are named in Mac. But otherwise the idea is anyway the same. So now I, at least myself, was wondering what happens if I after all delete exit. Like when you have main function, exit is present and you don't control what it does when it gets executed unless you call it explicitly yourself. And with main function you cannot test what happens when exit is removed. But when you have your own entry point start, then you can remove exit and see what happens. On Linux the program was just crashing. It was not able to terminate properly. On Mac somehow it continued working. To be honest, I don't know how. On Linux I do have an explanation though. The thing is, when you call exit, it's like a system call which never returns. So the process is just terminated. By the kernel, it will not continue after exit. It's not possible. When you have no exit, like the code just continuous execution, line by line, instruction by instruction. So imagine you have compiled this program on the slide. You had a entry point start, which was executing, then you get to the printf function, which executes, prints something. Next, after printf, there is something in memory, probably. There might be invalid memory, there might be some trash in the memory, filled with complete garbage from whatever was in the physical memory or something like that. Maybe it was filled with zeros, but there is something after printf. Like it's a big address space. It's very unlikely that your machine code is located in the last bytes of the address range from 0 to 2 in the power 64 minus 1. So probably there is something after printf function gets called, and the processor will just try to execute it, whatever is after printf. And I don't think it is something valid, because this is why we get the segmentation fault. If it was zeros or invalid memory, most likely, then you just get a segmentation fault signal because some instructions could not be executed because there are no any instructions. Now you understand what the process is, from where it appears, and how the processes are created, and how they exit, and how you can collect their status, and so on. And we also saw a little bit of the process resources, like it has some memory somehow, which is getting copy on write-it when you make a fork. But today I wanted to dive a bit deeper into the memory subject and into file descriptors. It also has other resources like EPC and signal queue, but those we will see at different lectures, as I said. From inside of a process, all the memory looks like a contiguous interval between 0 and 2 in power 64 minus 1. And in different processes, this interval will be the same. But those addresses, they are called virtual addresses, and this range is called virtual address space. They are mapped onto different physical memory pages, physical memory like sections in your main memory device. So it means that, let's say, the same address in two different processes can mean completely different things. In one process, it could be pointing at a string or a number, or be completely invalid, and in another process it would be pointing at a boolean or a structure of some sort, or also be invalid, right? Or it could be pointing at whatever else. They are not connected anyhow. Like this address range can be, it is the same in all the processes in the system, but it doesn't make them connected at all. They are isolated. And this is called virtual memory. Like memory layer is virtualized in a way that kernel for every process maintains some sort of mapping which virtual addresses for which process are mapped to which physical addresses. And due to that, it can easily happen, and it will probably happen most of the time, that the same virtual address in two different processes is just mapped to different physical addresses. This is what is happening by default, unless you on purpose want to share the memory somehow between two different processes. This mechanism of virtual memory allows to encapsulate details of memory mapping and how much physical memory you have in the system. Like this memory range between 0 and 2 in power 64 minus 1, it is very much memory. It's more memory than we have in the world combined. You probably don't have it on your computer, so doesn't mean that all this memory is usable. And also you don't need to think about how much of that memory is usable. You just use the memory and you let the system take care of how much how this memory is going to be mapped onto the physical memory device. How the memory translation works from virtual to physical addresses we will see at a different lecture, at the next one actually. From the user's point of view, so from ours, the memory is just a contiguous address space. We can just use those virtual addresses as we like. We don't need to think which of them are located in which section, are mapped to which physical space, which physical page. But from the kernel's point of view, each process's memory is a list of segments. Each is kind of mapped to different physical page. And the segments, they have meaning. Like it's not just some random data split into pieces. Those pieces have a special meaning, how they are supposed to be used. And from user space, we can even observe those segments as they are listed on the slide. It will depend on the compiler, will depend on the system, on the version of the system, on your hardware architecture, on the CPU. But in general, the idea is kind of the same for the sections that I have listed on the slide. In one way or another, they are present almost everywhere. And the sections are firstly env, like with no particular order. This section will store arguments of your main function and environment variables. Also, there is a stack segment, which will store surprise stack of your program, of your main thread. There is also a heap section, which allows you to allocate long-living objects, unlike with the stack. There is also BSS and data sections. They both store global variables. BSS stores uninitialized global variables, while data stores initialized global variables. We will see a little bit more on that later. And of course the text section, which stores the machine code. And there are more segments, but as I said, they are optional. For example, there might be a segment with debug information, multiple segments with debug information. There might be multiple heap sections. They might be called a little bit differently. There might be a section with strings. But anyway, they can be categorized kind of in the sections that you can see on the slide. Let's see what each section is storing. The section text is storing machine code, like literally bytes, which processor can understand and execute as instructions. And this will heavily depend on your CPU. what CPU do you have, what architecture it has. Text section is what the compiler is producing. It is stored in your executable file. It is probably mapped right from the file into the memory, and the processor just reads it byte by byte and executes those instructions one by one. Instructions are usually very simple, like the CPU, it cannot be logically very complicated in a way that it cannot do complex operations. What CPU can do is do multiple, many, like thousands of different unique simple operations, which can be combined together in a sequence to create something more complicated. The instructions will be very simple in a way that one instruction will say that I can add two numbers. Another instruction would be able to divide a couple of numbers. Another would be doing bitwise or writing into a register or writing something into the memory or loading it from the memory and so on and so on. Some vector operations. And there are literally thousands or even more of those unique operations which we don't write by hand. Compiler is just generating them for us. And this looks a little bit similar to the assembly language, except that it is even more low level and it's not text. It's literally machine binary code. The section BSS and the section data. As I said, both of them store global variables. Global, not only globally visible, but also like those singleton variables that are created once per process, such as literally global variables. You can see them on the slide, B, C, D. But also static variables inside functions, static members of your classes. Those things are going to be counted as global variables created once per process. And when you declare those variables with an initial value, like a equals 100, b equals null, c equals 123, d equals 200, they will be stored in the data section together with their initial values. And when the process gets started, the data section will be copied like from the file, from the executable file, and then you can change those variables in memory and so on. When the variables, the global ones, do not have an initial value, they will end up in the BSS section. Why the difference? Why not store everything in data or everything in BSS? Why do you need two? It's an interesting question actually. The thing is, when global variables have value, initial value, like which is something not zero, let's say 100, 200, maybe even with the zeros, but explicitly assigned, when you compile this code, those values have to be remembered somewhere. They have to be stored in the executable file, right? Because if you compile the code which has global variable a equals 100, and then this 100 has to be stored somewhere. So when you start the process, a will literally equal 100. If you don't store it anywhere, how will the process know that a should be equal 100? Right? So those variables, their initial values have to be stored somewhere. This is the data section. It will store initial values of those variables. When you declare a global variable but don't assign to it anything, like on the right side of the slide, static int a, cost star b, technically those variables have no initial value explicitly assigned by you, and also they cannot have just some trash values because it might be dangerous in case those trash values are anyhow connected to the physical memory which is given to you right now and was previously used by some other process, and perhaps it was storing passwords, for example. So you cannot leave those values as trash values, leftovers from some previous users of this physical memory that you got for your new process. That's why the global variables having no initial value will be all nullified when the process is started. And that means you don't even need to know any initial values or even how many of those variables you have when the process gets created. You just need to know their total size. So when the process is created, it can just allocate a block of memory of needed size where all the uninitialized global variables would fit, and it would simply nullify this memory, like literally memset 0, and it's done. So in the data section, you have to store the initial values to remember them, to be able to use them when process gets started. In the BSS section, you just need to store its total size, and that's all. That's why they are split into separate sections. Another section is the heap. It's one of the ways how to allocate dynamic memory. I say one of the ways because there are actually more than one way to allocate dynamic memory. It's not just heap. Malloc and new and are not the only ways to allocate memory, if you didn't know. It's just heap is the most used one. It is integrated into the standard libraries. There are standard out-of-the-box implementations how to work with the heap, how to allocate and free things, how to share it between the threads, how to do it all efficiently. And this section we commonly call the heap section. And it can have multiple sections, but we all can call them all kind of heap. Getting a little bit less simple, the heap implementation over time. Previously, I think heap section was literally similar to the stack. Like it was allocated once and then it was growing. And in some older courses you might hear that stack it's growing down and heap is growing up, and they can meet each other eventually if there is not enough memory. But in the modern applications I would say that heap doesn't grow anymore, like one section growing similar to stack. Instead you might have a heap section, initial one when the process is started, but then when heap needs to grow it will just allocate new sections in random places of your address space, and they might not even be called heap anymore. Or some applications will just write their own implementation of the heap and will not even use the standard one. Then you probably might even not have the heap section at all. But the concept of the heap, even if there is no literally section called like this in the list of sections, heap always kind of exists in any non-trivial application in one way or another. The standard heap, like this malloc or new function in C++, the common way of its implementation is a slab allocation. So when you take a section of memory, like you allocate a big one, let's say 1 GB of memory, you make it mapped to some physical addresses and you split it into blocks. Like firstly you split it in a few large 32 megabyte blocks. You also split it into a few 16 megabytes blocks. And in even more smaller 8 megabyte blocks, and so on until some very small size. And then you have this pile of blocks which are free, and when somebody calls malloc you give them one of those free blocks where the requested size would fit. So let's say you want to allocate 7 bytes. And malloc will probably find for you a free block of, let's say, 16 bytes. So it doesn't mean you will get allocations exactly as you have requested them in your argument of this size in malloc or new, but it will find a free block in this pile of blocks where your size will certainly fit. And will give it to you, and when you free the memory calling free or delete in C++, then this block will be marked as free and then it can be reused. Reusage, by the way, is an interesting thing which some people get surprised by when they write code and they have something they want to debug and they start printing pointers to see if they have any use after free or something like this. And sometimes you might see that memory was free, like you print an address which was just allocated, and then you do something and you free it, and then eventually you allocate something again and print the address and you get the same address as you have allocated before. This can easily happen because memory is reused. It's not like every malloc will give you a unique pointer and it will never appear again. It's not really happening. The memory is reused. You can free memory, and then when you want to allocate something again, you might get a block which you have freed before, maybe even in another thread. In the kernel there is one very generic way how to extend your physical address space, so to say, how to allocate new valid virtual addresses for your process. It's a system call called mmap. This is also used by modern heap implementations and by some other applications. Mmap is literally called memory map, and when you call it, it goes to the kernel and asks, please give this process more valid virtual addresses. So when they are accessed, the physical memory is actually under them accessible. And this way you can allocate memory for any usage that you like. You can say like mmap 1 gigabyte and use this gigabyte to split it into blocks and use it as a heap. Or you can say mmap 64 megabytes and use it for a stack for a new thread. Or you can use it for literally anything that you like. Otherwise, it is frequently used by custom heap implementations, by the standard heap implementation too. By the standard, I mean coming out of the standard library. There is no one standard way to implement the heap. But implementations of malloc, for example, they will probably use it. Also, malloc even will use it for large allocations, like when you want to allocate a really big block of memory, like for example, larger than 32 megabytes at once. Then malloc most likely will just call mmap for you. When you free it, it will unmap this memory back to return it to the system. Also, some applications, interesting ones like dlopen function. This function allows you to load dynamic library into your process and execute some code from it. How do you think this dynamic library is loaded into your address space? It is using a map function under the hood. How you can also explain a map? It's like a kernel heap. It's a way to get dynamic memory directly from the kernel. It's a very slow way because it's a system call, and we'll see why system calls are slow in the end of this lecture. But it is slow, and usually the user space does the following. It uses mmap either for something which is done very rare, like the open, or it uses mmap to get a large block of virtual memory from the kernel, and then it will split it into smaller blocks and reuse it in the user space like the heap does. In the kernel, the process memory is described using the structure mmstruct. It contains a list of segments with sections and their borders. And each segment is an object VM area struct. It's the first member of this mmstruct, and this is a list of segments. You can also see in this mmstruct thing some some borders of the sections that I have already talked about before. Like you can see the total size of the memory. I think it is total size. You can also see this list of sections. Literally, each section is listed here. It's like a doubly linked list, probably. And you can see the section borders of some of the sections. Like you can see the text. You can see data. BRK, it's basically heap. You can see stack. Note that the stack has beginning but has no end because it's growing. And there is also arguments, probably from the main function and env environment variables, but in fact I think they are stored in one segment these days. An interesting thing about how the stack is growing. Like you have been told probably that the stack just magically grows when you use it, and it shrinks when you don't use it. When you like return from the functions, stack will shrink. There is no magic really. Like when you try to ask how does this happen in details, what do you think? Like it's not a question with the lamp and points that you can get, but try to pause this video and think about how can stack be growing? What does it mean that the stack is growing? Because memory is limited. How long will it be able to grow? How does it grow in a way that it was allocated first, it got some physical memory, and then this memory was exhausted and you need more memory. How does this more physical memory gets allocated? How does it grow physically? Put it on pause and think. And the answer I will reveal right now. And the thing is, the memory doesn't just grow automatically. What happens is that when the process is started, your task, your first thread of the process, it gets allocated some default stack size, limited in size. And then you will be using this stack memory. You will put stuff on the stack, you will remove stuff from the stack. Eventually imagine that you have used this stack completely, like you put so much stuff on the stack that you have reached the end of the stack, and then you try to put something else. It means that Like the stack was a limited virtual segment, memory segment, and you just stepped out of it. Probably you stepped into a virtual address which was not mapped to any physical memory. What happens is that when the kernel notices it, like it receives this error from the physical memory device, it will see that the reason is that the stack was trying to grow, and then it will allocate an actual physical page for you. An additional one. Probably in some other place, like the stack doesn't even have to be one contiguous physical memory space. What does it mean, contiguous physical space? Like memory, it's not a ribbon which has contiguous segments. Memory is like a few memory banks that are hardware banks that are connected to your motherboard. There is no such thing as contiguous physical memory space. The longer you deep, the more you wonder. We will look more at the memory at the next lecture. I hope stuff will get clearer then, if it's not yet clear by now. And those VM areas tracked, they are also called VMAs. It's a common term, also used in literature, so it makes sense to remember it. Each of them stores start and end of the section, the links of the list, VM next, VM prev, the flags, like what you can do with this memory, like is it readable, writable, or whatever. And it also stores the where this memory is backed. So like what is the physical storage of the memory? Is it a file, or is it just the main memory device and it's not backed up by any file? It will be backed up by a file, for example, when for the segments such as machine code. So machine code is stored on disk in the executable file. You can map this executable code from file and it will be loaded in main memory, but the original is still on disk. Most of the memory though will usually be anonymous, so it will not be stored in any file, it will be just volatile main memory, which is allocated when you want and will be all freed when the process exits without any trace. And the flags will say like readable, writable, executable, shared. Let's make it a bit more visual. Like I said multiple times, the process has sections of memory. It has address space between 0 and 2 in power 64 minus 1. But this address space, contiguous one, is divided into limited size sections, which don't even have to be adjacent to each other. There can be gaps between those sections easily. And those gaps, those are virtual addresses which you can try to access, but they have no physical mapping. When you will try to access them, you will get segmentation fault. Segmentation fault error, what the name literally says segment. It means you try to access a segment of the memory which was not backed up by physical memory. That's why it's segmentation fault. Usually you don't think about it though, because all the memory you access in your normally written bug-free user space program, it doesn't try to access random virtual addresses. Usually allocate something, you work with it, with its members, you call some methods, functions, then you free it. You don't try to access some random number virtual address and think that it has any meaning, right? Or if you do, it's usually a bug. You don't do it intentionally. That's why those gaps between the memory segments, you normally just don't even think about them. But it is how the actual layout is looking like. Let's try to locate some of those memory segments, like to see them in real world, instead of just trusting me that what I am saying is simply true and you have to believe. When I was reading and studying those things, I wanted to check it myself, if it is really true. How does it look like? How can I touch it? How can I change it? Play with it? And I wrote this simple program, which creates some number of variables, global ones, local ones, and I wanted to see where they will end up, those variables. And some of the sections you can even see before the process is created, right after compilation. Right after you compile stuff, the program, some of the sections will already be stored on disk in your executable file. And when the process gets started finally, those sections will be copied into the main memory. But even before they are copied, you can find them on disk and inspect them. See some insights. Here is an example program which I compile. into an object file. So it's not an executable file yet, it's an intermediate representation, an object file, obj.o. And you can inspect object files or executable files on Linux using objdump command. There is a number of commands. Objdump is just one of them. On Mac, you can use gobjdump. It's basically doing the same. And we give it flags, -s, -d to dump the content of this object file and try to disassemble it. This is the output. It's a little bit unreadable, I would say. And it's very different on Mac and on Linux, but let's try to simplify it, because to me this at least looks unreadable. So I will try to make it simpler. I will just highlight the part of this object file which is relevant to us, and some machine code which is also relevant to us. And here is what we have. You can see that the section text in this file, which contains machine code, contains some random unreadable stuff, but also you can see some traces of the variables that we had in the source code. You can see here const char str4 and char str5. Not exactly as they are written in the source code, but you can clearly see them right here as symbols. You can also see the assignments 0x78 3 times and 0x20, 40 and 80. Those things. And those are those assignments, which are also available in the source code. So we kind of see that this resembles our original code, and we can even see some values from our code. And we see specifically the strings str4 and str5. This one and this one. But where is str3, str2 and str1? They are not visible here. So my question to you will be, where are str and str2 and str3? We saw that str3 and 4 are in section text somehow, and those are all just strings, right? Why aren't they all in the same section? The answer was revealed some slides ago when I was explaining the meaning of those sections, so you should be able to answer it. Try to pause video and think. And I will be revealing the answer right now. The str1, 2 and 3 will be in the data section because they are global and initialized. The 4 and 5 were not global. They were inside function, just local variables, not static ones on the stack. That's why they ended up in the text section. str1, 2 and 3 are in data. And the thing is, at least in C language and in C++ too, how you declare a variable kind of might make its value global even if the variable itself is not global. And also you have global variables which are literally global no matter how you declare them, and you have local variables which might have a global value. You can see kind of some examples on the slide. When you declare a string as like this, it's a variable s which points at a constant string abc. So you can reassign the variable to something else, but you cannot change its values because currently it points at a constant string. And the string itself might be stored absolutely anywhere, but it is going to be actually global. Most likely in the data section, or maybe it will be in some other compiler strings section or something like this, that bit is basically data anyway. We can call all sections like this data section. So the value is kind of global. When multiple variables like that will have this initial value, they might even get assigned the same address to point at the same section and the same string in the global section data. But the string itself, the pointer, this one, it doesn't have to be global unless you make it global, add here keyword static, and this variable can be changed to point at some other string. When you declare a string like this, You don't declare it as a pointer. You declare it as an array of symbols, literally right where it is declared. If you declare it inside a function like this, then it will be stored on stack. You can also make it global, then yeah, it will be global, stored in data, but when you declare it exactly like this, inside the function, it will not be global. And you cannot change anything, because const means you cannot change the content in this case, and when you declare it like this, not as a pointer, then you can also cannot change cannot make it point at something else as well. And if you remove the const, then it's also going to be stored on stack if you declare it inside the function, non-static, non-global. And you can change the content, but you cannot reassign the s to point at something else. So in summary, the str4 and 5 are in text, while str1, 2, and 3 are in data section. But something is not right. Perhaps I'm just messing with you. The str4 and 2 were declared in the same way. Why did they end up in these different sections? Let's look at the code again. The 2 string and string 4 declared in the same way. Both of them are declared as arrays, but they ended up in different sections. So think about the answer, pause the video, and when you think you know the answer, let's continue. And the answer is that because of different visibility scopes. So str2 was declared global, that's why it fell into data section. str4 was inside the function, it was not static, so it was local, that's why it was in the text section. Time to look at the stack. It's a type of memory which is used to store function arguments and local variables. And its features are, when we speak about program stack, it's high speed because how simple is the usage pattern. You just place stuff on top of the stack and you remove stuff from the top. It's not like it's randomly allocated some tree of blocks or a hash table, right? It's very simple. You put stuff on top, you remove stuff from the top. It can be implemented very easily in a way. It also has automatic allocation and deletion, so when you declare variables inside a function, you don't need to explicitly free them. You just call return, and the stuff gets kind of freed. And it grows down in a way that it's just some historical detail. I mean, there is no any specific reason why does it have to grow down. It's just something that was decided at some point and stayed like this. I think right now there is no any special reason why it does have to continue growing down. But a lot of stuff depends on that already in various binary APIs, so I don't think it will ever change. And the stack is reused in a way that, yeah, it can grow, like I explained a little bit before, that it can get new physical pages allocated, so contiguous virtual memory will grow and point at different physical pages, but it never shrinks. When you return from functions, it's not like some code gets executed that actually will go and free your memory or even nullify it. Stack can only really grow, and when it grows, there is a stack pointer, like a position, which is remembered where the stack position is right now, where to declare new variables and when to remove them from. So like the top of the stack position is remembered somewhere in the register, and it's literally just a number. It can go up, it can go down, but it doesn't really free anything when it goes down. It's just a number which grows and decreases. Decrease of the number of the current top stack position doesn't trigger any freeing of anything stored on the stack, which is a bit interesting and curious thing, which can lead to various effects, let's call them this way. Here is a program which I compiled from the previous example, so I took the object file, I compiled it, and I got the executable file. And the program was not only for testing where the global variables and local ones end up, it also is doing something. And what it's doing is that I declare a variable a on the main function in the beginning of it. And I print address of this variable to see where it is located on the stack. And then I call function testStack 2 times. The function testStack also has variable a and also prints the address of this variable. And then it prints the variable, and only after printing it, it gets assigned. And it happens 2 times, because I call this function 2 times. Then I call some other function. Another function which will do something on the stack, something random like create an array, fill it with zeros, print something. Function printf will also use the stack for a bit. And then I call test stack again. A question for you to think about is when I call test stack first time, what do you think will be printed here? And when I call it second time, what do you think will be printed here, and third time too? Like, what will be the output of this printf when I call it 3 times? Here, here, and here. Put the video on pause and think. And I will reveal the answer. I will just execute the code. Here is what was happening. Firstly, we can look at the addresses of the a variables, like address of this one, address of this one, and we can see that the stack indeed grows down, because address in test stack of its variable on the stack was a little bit less, because it was 9f8 became 9c8. So address of this variable was less the address of this one. It's a very simple way to check that stack indeed grows down. We can also see that variable a, first time I executed test stack, was printed as some sort of garbage. Like completely irrelevant value, which is expected because I printed it before assigning it. You see? Then I assigned it, and on the second execution of test stack, it was equal 10 before I assigned 10. And it's not like printf suddenly started seeing the future. Actually, printf was seeing the past. Because when you enter the test stack again, the function, it will happen most likely that all those local variables will be again placed on the same positions on the stack. And those positions still have values from the previous call of test stack, and it happened that a was mapped to the same position where was a first time when test stack was executed. And this is why you will see here 10. It is actually 10 from the previous call of test stack. But when you call it third time, after calling some other function, the stack is kind of spoiled. So the a was stored somewhere in the stack, then you call another function which will memset this stack and use it for its own local variables completely unrelated to a. And when we call a again, the test stack again, a will be 0, probably because I was memsetting it here to 0. You cannot rely on variables being unassigned and remain the same values when you re-enter the functions. But I hope this example explains how you might sometimes see surprising values in your variables on stack before you assign them. Another thing I wanted to say about stack and heap is that you should not think of a stack as something which is faster than the heap. Which is a bit counterintuitive, right? Because intuitively, most of the people, when I ask them, they say, like, you ask, what is faster, stack on the heap? And they think about it for a little bit, and then they say, probably stack. It's actually, both the question and the answer are incorrect. Because faster than heap for what, exactly? It's not like your just think about it at the practical level. It's not like the physical memory that you have in your computer is divided into what is stack and what is heap, and heap is slower, right? When you open your PC, look at the motherboard, at your memory banks, you will not see on one of them written heap, and then it's cheaper and slower, right? You just have all the same main memory used for the stack and the heap, the same physical memory. It works the same, which means access to already allocated stack or heap memory will be the same by the speed. Like imagine a function which is taking a pointer at some array or an object. The function will work equally fast if the object is stored on the heap or it is stored on the stack, because it is all just the same physical memory. The only difference in heap and stack is how are they managed, how are the blocks on them are allocated and how they are freed. It will be faster to allocate things on the stack because it is just much easier. It doesn't have to deal with concurrency because stack is usually for one thread only, like always for one thread only. And the pattern of freeing and allocating is very simple, because the allocation is basically you just bump one number, increase it, like change the stack position. While in the heap, you firstly have to deal with concurrency when you allocate and free things, because multiple threads will use the same heap, at least at some level of that heap. And also, the heap is just much more complicated data structure, because it's not just a contiguous virtual entry space. It probably will be multiple large blocks which are split into even more smaller blocks and smaller blocks, and they are organized in some sort of tree or a hash table. It will be just slower to look up for free to look up free blocks in the heap and to put back the free blocks, freed blocks. Right? So the allocation on the stack is faster than on the heap, but access to already allocated memory is the same. You will not be able to see any difference. If you don't believe me, you can benchmark it. Just make sure that the memory is allocated once and not like on every iteration of your benchmark loop, if you will really go and do it. The stack and heap and other very dynamic like runtime sections you will not see in an object file. In object file, you see something that has to be persisted in order to be loaded into memory later, like initial values of your variables or the machine code. Those things have to be persisted, obviously, because if your compiler doesn't remember them anywhere, then how will you execute them later? When, for example, computer is restarted, right? So they have to be stored on disk, which means they will be accessible in file. But stack, heap, they don't make any sense without a process, which means they are not really stored in a file. But in the process, you can still see them, and all the other sections that we have listed by now, you can also find at runtime as well, not only in the file. And in Linux, you can do that using the special file procs, then your ID, and then maps, like those folders. Folder procs, folder of your process ID, and then maps. The procs file system, it's like a virtual file system which is not stored on disk. It is actually backed up by the kernel. So when you open any folder or file in procs file system, it is actually you're just accessing some pieces of the kernel, not something stored on disk. It's a file-like looking API into the kernel internals, which is public, documented, and you can access it for monitoring, statistics, analysis, benchmarking, and so on. Maybe or even for some business logic. In our case, we want to look at the memory segments of our process, and the file maps will store the memory segments in text format. You can find and read them and try to analyze them. And in this example program, we will start a process which will print out its own section of its own list of segments of its own memory. And this is how the output you might expect to look like. This is like each line is a segment of virtual memory which is in the kernel mapped to something, and you can try to guess the meaning, or even meaning might be written right in the line on the right side. You can see the flags of each section, what can be done with it. Is it readable, writable, shared, and so on. You can even see its start and end address and analyze this for whatever reason. The first section, for example, we can guess it's a text section. Another one, this would be data section. Another one would be BSS. This is heap. This is something which is just mapped using mmap. So anonymous general purpose sections allocated for for the needs of the standard library, maybe for some DL open things, for the heap, whatever else. You can see the stack of the main thread, the env containing the environment variables and arguments of main. And on the right column, you can see what this memory is backed up by. In some cases, you will see that the memory is actually mapped from a file, from our executable file, or from the standard library, which is in our case a dynamic library, libc. You can see the linker library. You can even see our own source code here, because we mapped our own source code file, and we can now see it here in the list of segments. And for some segments, you might even get a name from the kernel. What do they mean? Like stack, var, vdso, vsyscall, heap, whatever they mean. And you can see how this all is mapped to VM area struct. Like literally some members of the struct are mapped to the values in those lines. The start, the end, the flags, the file or private data are stored here. This is the shared library segments, as I said, and those are the flags, which by the first letters you can guess what they mean. Like R probably means readable, V means writable, X means executable, P means private, or when it's S, it means it is shared. The S means actual shared memory that you can share between parent and child process. Literally, they will use the same memory. You can use it for some sort of data transferring between child and parent process, for example. We will actually try it on one of the lectures, but not today. But today we can have a look at some simpler example just to show that this shared memory segment indeed will not be copy on write. And I have a program, example program, where I allocate memory using malloc. So it's going to be private memory, and using a map with the flag shared, which will be shared memory. And then I initialized both of them first byte with the value 55. And then I make fork. In the child process, I will reassign them to value 56. Then I wait until the child process is terminated, and then I print the result, which are the first bytes of the shared and private memory in the parent. When the memory is copy on write, it means that it will be unchanged in the parent. If it is shared, it means it will be changed. So the child process actually affected some memory in the parent. And we can see that indeed shared memory was shared physically by two processes, but the private one was like copied when the child process tried to change it. At the beginning of the lecture, we saw one other memory segment for the environment variables and main function arguments called env. And we saw it in the maps file. And you also saw that in that maps file, I was able to tell where is text section, where is stack, where is heap, where is whatever else, other sections. But it was not written in those sections like this is text or this is some other section, heap or env. Right? Some of those sections had names, but others did not, and I still was able to deduct which those sections mean. And the way to do it is just in your program, you can simply print addresses of variables from different sections. Like I print here address of an environment variable, an address of the main arguments array, address from the stack, and address from the heap. And when you have those addresses, you can simply try to map them to the relevant ranges in the maps file. And if this address fits into one of those ranges, you can tell that this range entirely belongs to environment variables and main function arguments. The same with other sections. So it's just enough to find one address in a section, then you can find the entire section in the maps file and tell which of them is doing what. The environment variables, by the way, we didn't speak about them and we will not really speak about them more. But in case you don't know, it's a useful thing. It's kind of implicit arguments which are passed to every program by the parent process and which are organized in a key value manner, so you can get those variables by name. Like in this example program, I get a path variable using getEnv function. It's a standard function which will return you value of the given environment variable. And those environment variables you can use for anything you like yourself, use some random names, whatever. Or some of them have special standard meaning, like for example the path environment variable is a standard one which contains the paths by which the system will look for the executable files when you try to execute things like ls, grep and so on, or some other globally installed executables. And the API is relatively simple, so you can get those variables, you can set them, but setting them is something you probably should not be doing, because it's not thread safe API. I think there was a thread safe API how to do it, but I'm not sure. Either way, usually you just get those variables. You normally don't set them. Not in a multi-threaded program, absolutely. The last thing to say about memory. When you want to debug your program via a special utility like GDB or LLDB, you might also not want to debug assembly code because it's not too simple, not everybody can do it, and it sometimes can have very little links to the original code when it's heavily optimized. By default, your executable file will not contain any helper information, like how to debug it, which machine code is mapped to which source code. So when you use a debugger, you can like walk your program step by step by the lines that you wrote in the original code. By default, this debug information is not available, but you can provide it using flag -g. And normally you would also be expected to disable the optimizations, so the machine code matches better the source code. And then you can interactively debug using GDB or LLDB. For that, the executable file will contain some additional sections containing this debug information, like which parts of the text section are mapped to which files and lines of the original code. This is absolutely necessary, obviously, otherwise how would debugger know which of the currently being executed machine code matches to which function, which line in which file that you wrote originally, right? Usually this debug information is quite large, can be even much bigger than all the other sections combined in the executable file. That's why sometimes, like most of the time, people do not compile with debug info, or they do, but they strip the debug info into a separate file, and in production they run the executable file without debug info. And when the process, for example, crashes in production, it creates a core dump, which then can be joined with the debug information stored somewhere else and be debugged. It's a bit complicated topic, but I still wanted to mention the debug information for the completeness of the picture. Memory is not the only process resource. One another, and sometimes even more complex to understand, is surprisingly file descriptors, or file descriptor table of the process. You can find it in task struct, which has a member files, which points at files, struct, which stores fd table pointer, which stores the array of file descriptors. Each file descriptor in the kernel is an object struct file, and an array of pointers to struct file is stored in the kernel, and when you get a file descriptor in the user space, it's a number, as you know. This number is just an index in this array. And the file descriptor object struct file already stores some relevant information, like what this file is, what flags it has, and so on. Some of the descriptors are standard ones. They are defined out of the box and are available to you, unless the parent process closed them, but we will get to that. And those three descriptors are standard input, output, and error stream. And you can write and read to them, and they usually mean that stdout is something you print out, like it can be normally printed to a console or to a file, and stdin is something your program gets as an input, like interactive input usually it means, of some sort, and std error, it's basically the same as stdout, but it's different stream, and you can filter them out, for example, into different files. The existence of those descriptors means that you can write to them directly and read them directly. Like there are some functions which do it for you, like printf will write to stdout. or scanf will read from stdin. But those descriptors, those constants literally exist in the standard library, and you can also write to them directly using other functions or system calls like write. So here I wrote directly to stdout without any printf usage, and I got the output for both of those calls, right? So printf internally just also does, in the end, write stdout file now. Just does some preliminary string formatting, but then it will write to the output anyway, to the same descriptor. And you can open more descriptors using multiple functions like open, socket, accept, pipe, dupe, and many other system calls. They will create file descriptors. In Linux, Unix system in general, they do use file descriptors as not only for files, but just descriptors to describe some object. I would even say it's just most of the time the object is a file, but sometimes the object is a socket, channel to a remote machine, or channel to another process, or multiplexing tool for file descriptors like epoll or caq. We will see most of this stuff during the course. Today we will try to concentrate on them being pointing at files or pipes. We will see most of the stuff during the course at other lectures. Today we will concentrate on a little bit simpler stuff. Schematically, this is how file descriptors and files are linked. We can try to visualize it. I like to visualize. I think it helps to understand things, especially when you visualize it yourself. And imagine we have a couple of tasks, like maybe different processes. They have file descriptors, stdout, and they point to struct file in the kernel, which is going to be file descriptor. And if you open them literally physical files, then they will also point at something, like literally some file. The naming is a bit strange. We will talk about it more during the course. Those legacy APIs, sometimes the naming is very unfortunate. Like here it says struct file. You would expect it's a file. It's not. It's a file descriptor. It's not the file. The file is called struct inode. This is very counterintuitive, but you just have to remember it and live with it. This is legacy, there's nothing we can do with it by this point. But we will look at how the literally files are organized in a separate lecture. Today we look only at file descriptors. When you have stdout, it's also like normally a console where you print stuff and you can see it right in front of your eyes, and it also points at some object which describes the console. Again, we don't need to dive into that right now, but the picture is that different file descriptors will point at different struct file objects which can be backed up by file, can be backed up by console, or by whatever else. When you work with a file descriptor, like when it is intended for reading or writing, you usually try not to care much what it is backed up by. And let's see some trivial issues and not so trivial ones about working with files. Imagine we have this program where I want two processes open a text file and write their process IDs in the end of that file. So the file would contain process ID 1, whitespace, process ID 2. They will run the same code. So they just open text file, they get their process ID, then I make them pause, like stop for a second, then I will enter any key, and then I will print the PID of each of those processes into the file, and I will close the file. What do you think will happen when I run this program 2 times? So here I started it 2 times. They are both waiting for me to enter something. They have different PIDs. I pressed enter in one of them, and it wrote the PID. Then I pressed enter in another one, and it also wrote the PID. Intuitively, I would expect that now the file will contain the numbers 46152 and then 46153. 2 PIDs written with a white space between them. Actually, I will only see the second one. The problem is that when you work with files and you open a file, firstly, you will open the file from the first position in that file, like from the beginning of the file. So if the file already has something, you will just overwrite it. You will not automatically write to the end of file. Also, in this case, even if we would write to the end of file, It will not help us, because what will happen is that you start both processes, right? Both of them try to find the end of file, which in this case will be 0 because file is empty. Then, in one of them, I will continue the execution and it will write its speed into file. Then I will continue another process. It uses different file descriptor, which still has position 0. So it will also write to the beginning of the file and will overwrite the first speed. Even changing the position of the file in this case will not really help much. And to fight that, there is a special flag which you can give to open. The flag is called oappend, and it will make sure that every time you call write on that file descriptor, the kernel itself, before writing, will reposition the file descriptor to the end of file. So you will always write to the end of file, no matter what other processes are doing right now. A question to you. Why does not lseek plus write work instead of oappend? Oappend is a one flag you give to open, and then every write will always write to the end of file. There is another function called lseek. It's a system call which you give a file descriptor and a new position to which it should be repositioned. So technically we could do that. You start a process, like you open a file, you call lseek to go to the end of file, and then you do the write. Why would not it solve the problem which was appearing in the previous example? I even answered this question, I think, when I was talking on that slide. But anyway, pause the video, try to think, and I will reveal the answer right now. Because of the interrupts. I mean, the previous example, we were using this getChar crutch in order to pause the program, so we can run them both. So they both of them open the file, and then one of them continues and then another continues. Technically, you don't even need getChar for that. You don't need human intervention to get this data race. What will happen naturally, absolutely, without your participation in that is that the processes will be paused by the kernel simply due to scheduling. Like one process probably did open, then did lseek, repositioned to the end of file, its file descriptor, and then it was removed from the CPU core because it was running for too long already. Then another process is started, calls open, calls lseek, and then it is also removed from the CPU core because it was also running too long. And then the first one is continued, it writes to the file, and the second one is continued, and it also writes to the same place of the file, and they overwrite each other. So lseek will not help here. Only oappend can help, but to be honest, even oappend doesn't give you, I think, much guarantees, because write, when you give data to the write, the buffer plus size, write doesn't even guarantee you that the entire buffer will be written. So you cannot count on being able to write like 1 kilobyte atomically. You cannot really be sure of that. It could be that you try to write 1 kilobyte and only, let's say, 512 bytes are written. And what do you do? When you try to write the next half, it will probably be already separated from the first half by some other process easily. So it's this open doesn't really fix the underlying architecture issue that you are having if you depend on this kind of stuff. It was an example how like the same file, literally physical file, can be pointed to by different file descriptors in different processes. If it would be just that simple, there are many more ways how to organize work with files and file descriptors and how you share and duplicate and reference count them. Let's start with a little complication. There is a system call called dap and also dap2. Those are two different system calls. And dap system call is like standing from duplicate. It takes a file descriptor and it creates duplicate of that file descriptor. Duplicate means that it will be another reference to the same file descriptor. Just let it sink in. You will get a different number in user space, which looks like different file descriptors, but both those numbers will point at the same struct file in the kernel. Like this struct file will literally be stored 2 times in the array of file descriptors in the kernel. And this is easy because this array stores pointers. So this pointer at struct file in the kernel fd table can be just stored in two places, easy. And it will probably be reference counted, so the kernel knows when it has no references and it can be deleted. Which means the file descriptors that we have in the user space, those numbers, they are not even direct file descriptors. They are just references to some file descriptors. And some of those different numbers, fdo1 and fdo, are like two different numbers. They can be pointing at the same struct file. And this struct file can be anything. Can be file, can be a console, can be a socket, can be whatever, anything else. This API works with any file descriptors. So dup will just return you a new file descriptor, a new number, a random one, like not completely random, but you don't usually control which one. Dup2 allows you to choose the target file descriptor. So you can say that I want this file descriptor, this number, to be duplicated into this number, into this file descriptor. If the second one was already open and busy with something else, then it will be closed. And you will have, like with dup2, you have complete control what will be the second number pointing at the same struct file. And this dup thing, like it looks very stupid, but it's a foundation for building the pipes. Pipe is this vertical line that you can see in untrivial bash commands. When you can connect output of one program to the input of another program. That's why it's called pipe. It's like pipe which transfers output of one process into the input of another process through this like imaginary pipe. And dup is the foundation for that, for connecting two processes like this. And for that we also will need the pipe system call, but about it a little bit later. Let's firstly experiment a bit with dup. So here I opened file, some random text file, and I also duplicated this file descriptor. So I have fd and fd2. And I can easily test if those file descriptors are actually one. I will write to the second one and close it, and I will write to the first one and close it. If those would be two different file descriptors, like I would call open two times, then 2 would override 1. Because when here I wrote something using fd2, the position of fd would not change. But if they are the same file descriptor, then I will see in the file written 1 and then 2. And this is what I will indeed see, which means those two file descriptors are literally one file descriptor. Just two references at the same file descriptor. Another question to you, related to our pipe topic, is what happens with file descriptors after fork? I don't think I have revealed the answer during the lecture, but it is something you can deduct for yourself if you think about it a bit more. So try to pause the video and think. What happens when you have descriptor, any file descriptor in the process, and then you call fork? How will the child file descriptor and parent file descriptor be related? And will they be related at all? And I reveal the answer right now. Nothing happens, they are kept as is. The thing is, when you call fork, it's like all the file descriptors in the parent process were duplicated. So they will be one descriptor, but multiple references to the same descriptor. Imagine parent opened the file and got a file descriptor fd. Then you call fork. And then fd also exists in the child. fd in the child and fd in the parent will be two different references to the same file descriptor in the kernel. They will literally share one struct file. And you can use it to your advantage for some interesting scenarios. Let's firstly test if it is indeed working like this. Here again, I created opened the file, text one. I duplicated the file. Then I created a child process using fork. I closed one of the descriptors and wrote something to another one. Then in the parent I closed another descriptor, waited for the child to end and wrote something to the another descriptor. And when I print the result of what is stored in the file, I will see that it stores both PIDs. Which means this FD, this FD2, and this FD2, and this FD, there are 4 different references to one file descriptor. And you can close those references, but it doesn't close the file descriptor until all the references are closed. And this is how it will work schematically. So you have 2 different processes or tasks, and they simply have the same references to the same file descriptor struct file, which is pointing to something, file, console, whatever. And there is another system call, which will open us the way to build complex pipelines of different processes interacting with each other. It's a system called pipe, which creates, surprise, a pipe. What does it do is that it takes 2 file descriptors and it will, when return, make so the file descriptor with index 1 in this array, you can write to that descriptor. And what you will write to that descriptor, you can read back from the descriptor fd0. So you write here, and you will read the same from here. This is like 2 ends of the pipe. This is input of the pipe, this is output of the pipe. This looks very useless. Like, what would be the point of that? Why do you need to transfer data like this? The point is that you can make so fd0 is in one process and fd1 is in another process. And then you can send data from one process to another. Let's test. So here I created 2 channels, 2 pipes. The pipe is unidirectional, so you can only write to one end and read from the other end. You cannot do it vice versa, which means if you want to send data from child to parent and from the parent to child, then you need 2 pipes. So here I created 2 pipes, to parent and to child. And then in the child, I close the unused ends of the pipes. I have to close them. You cannot leave unused ends of the pipe. Otherwise there will be problems, we will see them later. Then I read data that parent will send to the child. I print it and then I write response to the parent. So the child receives data from the parent and sends response. And here is what parent is doing. It is also closing unused descriptors. Then it will write something to the child. And then it will read the result from the child. And then we print whatever was done, and then we wait until the child is terminated. And it works. Look, we were able to send hello1 message to the child and receive hello2 message from the child. So the 2 processes are communicating. And I just needed 2 channels for that, and I needed to close the unused channels absolutely, otherwise there will be problems. This is how it would look like schematically. Like when you did 2 pipes and created fork, this is how many references you will have. You will have 8 references at 4 file descriptors. And this is when they are all open. We don't need that many. We just need a way for the child to send data to parent and for the parent to send data back to child. We don't need so many edges in this graph for that to be possible. So let's close not needed edges. Close those 2 and close those 2. Now we have a loop. We can, from the parent, write here, and it will be delivered to the child here. And we can also, from the child, write to this pipe, and the parent will read it from this end of the pipe. Now we have 2 unidirectional channels. You can write to one, read from another, and the same in another process. This example on the slide in front of you shows why it is important to close unneeded ends of the pipe. Let's see, so I decided just not to care about the unused ends of the pipe. I created a program while I have 1 pipe. and I take a command line argument if I need to close the unused ends. By default, I will not close. Then I create the pipe, I create the child process, and the child process will read the reading end of the pipe while it is readable, and then it will return. The parent will send the message to the child and then wait until the child is terminated. This is very simple, right? We would expect that this value is delivered to the child, then child terminates, and then parent waits for the child to terminate and exits. But the program will hang. Let's see. We see that the child was started. It read 100 bytes, like 100 message, and then it hangs. Nothing happens. The child doesn't terminate, and the parent still waits for the child to end. It's a deadlock. But if I give the close command line argument right here, then I will close the not needed end of the channel in the child, and like, for example, here we close the writing end because child never writes anything to the parent, right? So then we have to close it, just so because it's not needed. In the parent, we will write something to the child and then close the writing end, because we are not going to write anything else to the child. Using this close, we kind of give a signal to the child. The pipe has no writer anymore, which means there will be no more data on it. And this allows here in a loop, like first read will receive 100, but the second read will return 0. 0 means end of file, so the pipe is not readable anymore. And this while will exit, and then the child can finally return. And we can see that the program is not stuck anymore. This is what you absolutely have to do. When you are working with pipes, always close the unused end of the pipe right away. To see which of them are unused, like if you need some help, you can try to visualize it on paper or in a text file, how which processes, which needs of the pipe will need, and close the unused ones right away after fork, or after you finished writing, you close the writing end. After you finished reading, close the reading end. So we saw pipe, we saw dupe. Let's see how dupe 2 is working. This is the last step, almost the last one, before we can build actual pipes between different programs. Dupe 2, as I said, allows you to choose the target descriptor which will be replaced with a new reference to the first argument descriptor, right? And you can also choose standard descriptor as the target one. So in this case is what I did. I created a pipe and I made so reading end of the pipe is replacing std_in. And when the child process after fork will try to scanf, so read from std_in, it will actually read from the reading end of the pipe. And in the parent, I will write to the writing end of the pipe. And it will work. So as we can see, in the parent process, I wrote to pipe. And the data I read from standard input in the child process. Because the standard input I replaced with the reading end of the pipe using dupe 2. And one last step before we can finally build cool complex pipes is the function exec, which we didn't see so far. We didn't use it, at least. We saw it, but we didn't use. It's a program which takes executable file and arguments which will be given to its main function, and then potentially environment variables or some other possible arguments. There are many exec functions. I am using here execlp because this is the function which works like when you type commands in bash. It will search for the executable file in the same places. And in this case, I wanted my child program to execute Python program interactively. I give here, note that I give Python free 2 times, because this is path to the executable file. And those are arguments to the main function. I think all of them are actually are. They just need to end with null. And the agreement, the standard one, at least in Linux, is that the first argument in main always has to be the path to the executable file, how it was invoked. So the first argument here usually is supposed to be exactly the same one as the path to the file. So in this case, my child process is actually an interactive Python process. And the parent will send it a Python command to print result of 100 plus 200. And it will work. I will see that parent send this expression to the Python interpreter in the child process, and the child process printed something and then it exited. It exited because I closed writing end of the pipe. And Python then exited gracefully because it knew there will be no more input. There are many exec functions, as I said, we used this one, but there are more other ones and they allow you to do different things like where to search for the binary files. They might allow you to give the environment variables explicitly or the command line arguments in different formats like as variable, variadic arguments or as an array of arguments, whatever you like. You just have to choose the one which suits the best, and for that I suggest you read the documentation. It doesn't make so much sense to memorize them by heart. You can instead look them up every time when you need them. Besides the file descriptor table, fork will also copy the task struct itself. It will copy the list of memory segments and mark them for copy on write, but the data in the segments will not be copied, not right away. The user identifiers, which means that the child process will be running under the same user as the parent. Signal handlers and masks, we will see that separate lecture. Resource restrictions like limit on memory or number of file descriptors open. And the working directory path, so the dot folder, where is your working directory on the current process, it will be the same in the child as it was in the parent. The fork will not copy file logs. We will see that lecture about file systems and advanced I/O. Also signal queue, we will see it at signals lecture, and threads, we will see them at threads lecture. Not much we can say otherwise right now. The EPC objects also belong to the process, like they might belong to the process, or process might be referencing them, but we will not be able to dive into that right now. It's a big topic. For that we have a separate lecture as well. Here the process resources overview is completed at a degree to which we were able to complete it with our current knowledge. Next, I will shortly tell you about process interrupts. An interrupt happens when either a scheduler interrupted the task because its time slice was finished, or a more prioritized task appeared, or an exception has been raised by the kernel or hardware, or a signal has arrived. Exception, I don't mean like C++ exception. I mean a more low-level hardware exception. Exceptions are very different in types, reasons, originators, like what triggered them, but usually they all appear somewhere from the hardware. For example, it could be an exception of the type division by zero. The CPU cannot do that, it will raise an exception. Or foreign memory access, like segmentation fault, or invalid pointer dereference, or invalid instruction, or stuff like that. Hardware will notify the kernel about most of those exceptions happening, and the latter can either handle the exceptions or propagate them further to our user space, and we can then handle it sometimes as the signal, or we cannot handle it and our process is terminated. This is what usually happens by default. For example, imagine a stack of the main thread is completely used. Then it can be extended to continue the execution by the kernel automatically, and we will not even notice that. Or a write happened into a page marked as copy on write. Then the kernel will handle it also without notifying us. We will not even see that. But some exceptions are critical and they will require our attention, or even might just kill the process without giving us any chance to handle it. Like segmentation fault is a happening when we are trying to access invalid memory, and then this signal you can usually handle. Here I have an example where I try to trigger such an exception. I have code where I have some local variables and I have a buffer on the stack of size 100. And I try to access this buffer by the index 10,000, which will most likely go into some invalid memory segment because it's very far beyond the array borders. And this, again, most likely will trigger a segmentation fault. It will be an exception on the CPU that it could not access this given memory, and this will trigger an interrupt in the kernel, and it will send me a signal which I then can handle or I will not handle. In this case, I did not. And then this kind of exceptions sometimes can produce artifacts that you can debug. For example, if you allow in Linux the kernel dumps, you have to usually, like normally this is done using ulimit command. You give the command that the core dumps can be of unlimited size, or whatever size you choose. I usually choose unlimited. And core dump is an artifact, like it's a memory dump of your process, which will be created by the kernel as a reaction to certain errors or signals delivered to that process, like a segmentation fault. In this case, a core dump was created because I allowed it, and it was printed that it was dumped somewhere. You can also do it on Mac, by the way. On Mac, in modern Macs, it is very complicated. You have to sign your executable using some commands and then do the same ulimit -c unlimited, but then it will work. You can Google how to do it on Mac. I will not repeat it because it gets changed like every release. But on Linux, it is relatively stable and simple. So here I created on purpose a segmentation fault, and there was a core dump created. Here it was on Mac. Like this is where Mac will store core dumps. By default in Linux, I think it will be stored in the same folder where executable file is. Or well, the work folder of the process was. This I don't remember, to be honest. And then you can load those core dumps using a debugger like LLDB or GDB. And you can inspect the state of the program when it ended. Like you can see, for example, the backtrace where what was the stack, the call stack when the process was terminated. You can also go to different frames of that stack, like to frame 0 to frame 1, and inspect local variables, arguments of the functions, and this usually helps you to debug how did the segmentation fault happen. This is a full core dump which will contain the entire heap, all the stacks from all the threads. This is full information, but usually very helpful, but you need debug information for it available. The file with debug info, either separate or inside the executable file, debug info should be present, then you will be able to see the source code even. There is also another way, not full core dumps. There is a thing called mini dump. The thing is that full core dump, it's like literally all the memory dumped into the disk. And if you had, let's say, 100 gigabytes process, a database, for example, then a core dump will take like 100 gigabytes. It's a big file. It's not very simple to store it, to transfer it. And if a lot of them are being created in some sort of crash loop, then you will quickly use quite a lot of memory. So the solution is that sometimes in projects like that, people either create stripped core dumps. It is possible using some APIs, or there is a way called mini dumps. It's a special format of dumping memory and local variables and other stuff, which is invented by Microsoft, and it's very minimalistic. That's why it's called mini dump. And it will not dump all the memory. It will dump only very limited memory, like some stacks, maybe some local variables, but it will not dump the heap. It will not dump many other things, and you have to explicitly add things to it during the runtime, so it would be dumped if crash happens. But it's a big topic, like in general, crash handling is very untrivial, surprisingly. There is a lot of stuff, how to do things. And usually it's something you choose for one project, or it's already chosen before you even came to that project and you just have to stick to it. doesn't make much sense to dive into it into super details. Everything seen so far was work from user space point of view. All of these examples and standard library functions, which under hood can be system calls. But how do pipe, EPC, open, close, and fork interact with the kernel to execute some code in the kernel context? Like pipe, if you think about it, it's a very low-level thing. It's connecting two isolated processes with each other, which normally don't know about existence of other processes at all. Like they have isolated virtual memory address space. They don't know even how many cores we have in the system, or they don't need to rely on that. This is all abstracted away from them. Everything is isolated and virtual, and there is a way to connect two different processes together so they can send data to each other, or even we can share memory with them using a map system call with shared flag. How does it work? You need something below user space, below those processes, and this is the kernel, and you have to tell the kernel what you want, and this is the system calls. System calls is a way to access certain functionality of the kernel, which sometimes allows you to do untrivial advanced stuff like different processes interacting with each other, or one process going to the network. Basically, any time when you want not to just count some numbers in the process, you will probably end up doing a system call. To open a file, duplicate a descriptor, talk to another process, work with the network, this is all going to be system calls. And also system calls are reason for many compatibility issues because their count and behavior can very much differ on various systems. Because indeed, like system calls, as I said, I think on the 0 or first lecture, is API of the kernel. When you have different systems having different features, purposes, they will have different APIs. Like, for example, Windows kernel, Linux kernel, absolutely completely different things. They will have different APIs, different system calls entirely. However, the good news is that usually system calls are all hidden behind libraries APIs. Like the standard library will implement a lot of system calls for you, access to them, so you don't need to think whether you run on Mac, on Linux. On Windows you usually have to think. But if we work, for example, with C++, then you can kind of write a lot of code in just one way, and it will work the same on Windows, Linux, Mac, and other systems if it's not too low level, right? So the libraries for each system, they will abstract those system calls away from you, which doesn't mean you don't need to know about system calls. In the Linux kernel, we can kind of investigate those system calls very closely because it's all open source. So you can just open and find those system calls in the kernel, and there are not even too many of them. In the Linux kernel, the system calls are implemented as C functions, at least most of them, and you can find the list of the calls in one file somewhere in the kernel where all the system calls are listed. And each syscall has a unique number. This is not even unique Linux specific. All the system calls always have a unique number in different systems too. And user space, when it wants to invoke a system call inside the kernel process, it will tell the kernel the number of the system call which it wants to get executed. Not a name. Like those system call names is just for us. The kernel is for the communication with the kernel goes at a much more low level than that. It's not like you send the request to the kernel with the system call name. It is rather done by identifiers. All the system calls have unique IDs, and your user space process can tell the kernel that I want system call number 65 to be invoked with some arguments. And even if the system call is deleted from the kernel, which is happening rarely, because it's like breaking backward compatibility, kind of. If you have program compiled for an older kernel and then in the new kernel the system call is deleted, and you run this program, then how will it work? It needs a system call which is deleted in the new kernel, right? So deleting them is kind of a big deal. And even when it does happen, the system calls will be, like their identifiers will stay reserved. For example, you can find some of them in the kernel even now by the identifier sys ne syscall. Like ne means not implemented. So they deleted old system calls, they just get this like placeholder, which will simply always return an error. And then the user space program is supposed to react to that gracefully. So the old programs will of course break when their system calls disappear from the kernel in new versions, but at least they can break like gracefully, right? In an error message or something like that. And familiar system calls we can also find here implemented just fine. You can see their implementation. Sometimes it is even short and understandable. Like dup2, you can find it as sysdup2 in the kernel source code and find its implementation. A question for you. So there is a user space which wants to invoke a system call by some number in the user space, in the kernel space, in the kernel process, literally. How do you think this could be working? So again, we have one process in user space, another process in the kernel itself. We want in user space process invoke some code in another in kernel process. I suggest you to pause the video and think about it, some ideas. How would you do it if you had to? And keep in mind that it cannot be too complicated. I would not ask you something which is like super complex if I didn't think that you would be able to guess it, to answer, to try to find it. So I am saying the answer right now. One way would be using via registers and a special interrupt. So we know of at least one way to enter the kernel. It's interrupts. And every time when an interrupt is happening, a kernel handler is invoked. So if we could just somehow in a user space process trigger an interrupt, then we would be able to enter the kernel context. And the specific system call we could, for example, identify as a number placed in a register. Right? The register in the CPU, we could just save the system call number in that register, trigger an interrupt, and the kernel would know that this interrupt, specific one, means system call. It would take the number from the register and execute the code that we wanted. Or maybe via a special processor instruction. This would also be the way. A special instruction available out of the box on the CPU, which you just call and you enter the kernel context. Would also be very convenient and even simpler and faster, right? Both of those ways actually exist. There are at least two ways. So, interrupts and special processor instruction. The first one, this interrupt way, is very old and it's kind of a crutch done in a creative, interesting way. And this is how it's working. So there is an instruction on the CPU called int, which is literally means interrupt, and it takes one argument, number of the interrupt to invoke, like to trigger. And the kernel can register interrupt handlers for all the unique interrupt like IDs. In this case, this number is 128. So this command will invoke interrupt number 128. And the kernel just has to register an interrupt handler on the interrupt 128. And it will treat this interrupt as a system call. It's just something that was agreed by the Linux community or whoever implemented it first time, maybe even by the Linus himself. It was just decided that let's choose interrupt number 128 as the system call interrupt. And we will trigger it in order to execute some code in the kernel. And the number, like unique ID of the needed system call, we will place on some register. Some system calls also have arguments. With them we can place also in registers or on the stack of the process, for example. Doesn't matter, there is a way to transfer data, it's just the most complicated part is how to transfer control in the kernel, not the data. And this way of triggering system calls is called a trap. So we like create a trap in which we step on purpose and trigger a system call. The system calls, like, it's not the only interrupt, there are many interrupts. is just one of them is chosen as the system call. And the handler is registered by the kernel when the kernel is started for this specific interrupt. And then it will execute code and give us back the control when the system call is done. Unless it will exit. The exit system call will not return us any control. This is a bit slow though, because this old way of system call execution it's a lot of steps, as you can see, right? Firstly, it's not even about the steps, it's literally a crutch, right? We literally have chosen some random interrupt number to use as a system call. We could as well use like 0x79 or what, like how was the number chosen? It's just a random number. Also, the interrupt handler for this system call interrupt, it is stored in a table of other interrupt handlers. There are many of them, not just one. Like there are at least 128, and actually I think there is even 255, 56 even. And they are stored in main memory. This array of interrupt handlers, it is stored in main memory. Which means every time when you want a system call, the kernel has to look up the interrupt handler in this array of handlers and then give control to that handler, and then it will appear in this system call handler in the kernel. The second way to execute system calls is more modern, it is faster, it requires less steps, but the principle is the same. Like it's a special instruction called sysenter, syscall, and the main difference is that it just skips the lookup of the interrupt handler. So it's like a special interrupt which is moved out into separate instruction, but otherwise the principle is the same. And the handler of this system call thing is just one register, not a whole array in main memory, but literally one register directly on the CPU, where the kernel will place the address of the syscall handler when it gets started, the kernel itself. So it's just faster. We don't need to go to the main memory. Here we had to go through the main memory, which can be slow. And here we just were able to only use the fast memory directly on the CPU, the register. About memory we will have a next lecture. I will explain more about how registers are working and why is main memory so slow. How are the arguments passed? It's not a big brainer, so to say. There are at least two ways. Like if you have few arguments, then you can place them on registers and the kernel will read it from there, or you can place them on your own stack. And given that the kernel has access to your stack anyway, so it can just read them from there. From registers it will be obviously faster because the kernel will not need to access main memory then. Otherwise there isn't really even much to add. About arguments, I would only say that the order of giving arguments to functions can be different in different systems. Like in Windows it's one order, in Linux it's another order, and the agreement that like the instructions syscall, sysenter, they will be also used by Linux, by Windows and by Linux and by Mac. But the implementation of the syscall handler will be different, and the numbers of the system calls will be different. Different systems and also how you pass the arguments can be different. It will depend on the system. But the hardware, the most low level where no code is being executed written by operating system authors, maintainers, this level will work the same in all the operating systems. While we were dealing with memory segments in proc maps file, one of the segments I intentionally ignored then, the segment VDSO. It's called Virtual Dynamic Shared Object. It's a kernel library, kind of like fake library, which is mounted by the kernel forcefully into each process when you start the process using like fork, and which stores helper functions to execute some system calls. Plus it maps some safe parts of the kernel into your virtual address space of your process to avoid syscalls completely for some things. Like for example, when you want to get the current time. The current time is probably some counter stored in the kernel in a global variable what you can do, what the kernel can do and what it actually does to speed up for us the getting of the current time is that this piece of memory will be literally mapped into our user space processes physically. So some virtual addresses in our process actually will point at physical kernel memory. And then from that memory you can just read this time counter without doing a system call, without this int 0x80 or syscall sysenter things. You can just directly read some stuff. And this is much faster. This is like order of nanoseconds versus order of microseconds. This is kind of the speed difference that you will expect from this optimization. Windows works similarly, like the processes and instructions, syscall sysenter, int, they don't depend on the operating system. The syscall sysenter do not, but int 0x80, it's Linux specific. On Windows there was another hack how to handle this, how to trigger an interrupt, but the idea was the same anyway. But I wanted still to say a couple of words how system calls in Windows are handled in general, the whole pipeline. In Linux you just call it, and that's all. You can either call it directly yourself in the code, or you can use the standard library to invoke some common system calls like read write and so on. Windows is a closed source project that does not expose not only its source code, but even system calls numbers, which means you cannot use them directly in your code. You can try, but it will just break in the next version of Windows, probably. Because Windows at different releases will mix those system calls, will change the numbers, will deprecate some of them without any backward compatibility. And you should not in Windows work directly with the system calls. Instead, in Windows, everything should work with the kernel using special public and documented DLLs or dynamic libraries, which will provide access to the system calls. And this is like one of the key components of the Windows in a way how it is so much actually backward compatible. Like you can have an executable compiled on Windows 98 and then run it on Windows 11 and it will just work. How is it even possible, right? On Linux, I wouldn't be so sure it would be able to work at such a huge distance of major versions. In Windows, though, it is actually possible to run some very old executables because there is this layer between the kernel and the user space, like our own code, which is those special DLL libraries which you have to use in order to access the system calls. And I think maybe in some new versions they just implement some deleted stuff. For the older versions, instead of kernel, they implemented directly in those DLLs, perhaps. And this is why they can compensate missing or changing functionality. But this is just my guess. Let's summarize what we have learned today. We firstly saw that the process is a resource virtualization mechanism. It hides from us things like physical memory, how it's organized, what's its size, what is its physical nature. It hides from us system calls, the presence of the kernel, the interrupts, number of CPU cores, and so on. We're like completely isolated and don't know anything about the hardware of the environment. By default, at least. This was the idea. New processes are always cloned from other processes. There is a single common ancestor for all of them, the init process, and all the others are created as forks of the other processes, of the parent. Also, process has multiple memory sections for different purposes like main, stack, the heap, dynamic libraries, global variables, command line, arguments, and so on. And you can see them, some of them even already in the object file, executable file. At runtime, you can see them in the maps file. File descriptors are not only for files. File descriptor in general is just a descriptor. It describes some entity. It can be a file, can be a socket, can be a pipe, can be a standard input-output, which underneath is actually also a pipe. And this way you can communicate with other processes on the same machine or even on different machines if it's networking. You just have to be careful when you're using pipe and dup2, how to close the unused descriptors and how descriptors are handled when you when you call fork. Processes communicate with the world using the kernel. Kernel is their only way to talk to other processes and to use the hardware in any way. Absolutely, otherwise the processes are completely isolated. And the only way to talk with the kernel is using system calls. System calls is like sending a request to the kernel, in a way, like through the CPU. You call a special instruction on the CPU, it triggers an interrupt, your process is paused, like your thread is paused, your task, and then the kernel will execute the function that you wanted by the unique system call ID that you gave it using a register. Next time we will talk about memory, how it's organized, the virtual one, the physical one, how it's working. We talk about the CPU cache, the user and kernel memory and false sharing problem, and more.